Precious metals like silver and gold are unreactive. This makes them ideal for making jewellery and ornaments. At the other end of the spectrum, metals like lithium, sodium and potassium are so reactive they can be dangerous. But there's a wide range of metals in between, and seeing how they behave in different solutions can help put them in order of reactivity. Placing the metals in lead nitrate solution provides our first clue. Silver doesn't react, and neither does copper, but magnesium and zinc both become coated with a dark grey layer of lead. Magnesium and zinc are displacing the lead from solution. Placing zinc metal in a magnesium solution and magnesium in a zinc solution will help determine which of these two is more reactive. Nothing happens to the zinc strip on the right, but magnesium reacts instantly, displacing the zinc from solution. Magnesium is the winner. It's the most reactive. But which is the least reactive? Silver is placed in a copper solution and copper in a silver solution. The silver strip doesn't react, but the copper immediately displaces the silver. You can actually see crystals of silver growing on the copper strip. After several hours, there's so much silver it glistens, and the colourless solution is starting to go blue. So, magnesium is the most reactive and silver is the least. What would happen if you placed a strip of magnesium into a solution of silver nitrate? Chemical reactions tell us about a metal's reactivity. Mix zinc with copper oxide, lay the mixture out on a heat-proof mat and heat one end. A reaction soon begins and spreads through the mixture without further heating. Zinc is reacting to form zinc oxide, which is yellow when hot. But what else has formed? Place the remaining solid in dilute acid and after a few minutes you can see pure copper. Zinc has reacted with the oxygen in the copper oxide, leaving copper behind. So zinc is more reactive than copper. Aluminium is another reactive metal. Its reaction with iron oxide gives out a huge amount of energy. A measured amount of aluminium is mixed with iron oxide and placed in a small pot. Potassium permanganate is sprinkled on top, and glycerol is added. The vigorous reaction between potassium permanganate and glycerol gives out enough heat to start the main reaction. Red-hot molten iron falls into the bucket. The aluminium has reacted with the oxygen in the iron oxide, leaving iron metal behind. So aluminium must be more reactive than iron. This reaction is so effective that it's used on a larger scale for welding iron railway tracks together. molten iron fills the gap. And a grinder makes it smooth.